Boom! Yes, folks. So welcome to the second video in our series on surds. In this video, we're going to look at the idea and the concept of simplifying surds. Alright, and as we ended the last video talking about the perfect square, you will see that that concept of the perfect square is core and central to the whole idea of simplifying surds. Let me explain what I mean. So let me deal with the same numbers we have on the board here. Right? These are the surds that we would have had as a result of the discussion in the previous video. So we clear the board and we leave them up because we want to talk about these fellas here. Now, we want to use these fellas to illustrate what we're talking about. So we could take the square root of 5 and we could say that the root of 5 is equal to the root of 5 by 1. Right? So in other words, 5 being a prime number, you can't really break down 5 any further than that. Right? We had a whole video before we spoke about prime numbers and factors and multiples and stuff like that. The square root of 8, we can say that the square root of 8 is the same thing as the square root of 4 multiplied by 2. Right? 8 is 4 by 2. We could leave it as 4 by 2 for now, and you will see why I chose that particular factorization, that particular breakdown. We can say that the square root of 18 is equal to the square root of 9 multiplied by 2. And then we can say here that the square root of 22 is equal to the square root of 11 multiplied by 2. We can say that too. Yeah, why not? Alright? Now, this doesn't really do much. There's nothing else we could do with this in terms of breaking it down. So root 5 is root 5. We leave that so. Root 22, same story. So the number 22 could be broken down as the product of 11 and 2. 11 by 2 is 22. So root 22 is equal to the root of 11 by 2. You can't really go any further with that. However, with these two fellas here, we have a little trick, we have a little tweak. And this is what it is. Because using the rules of indices, and I will give you all a brief reminder of the rule I'm going to use now. We can express this further as the root of 5 multiplied by the root of 1. We can do the same thing here. That is equal to the root of 4 multiplied by the root of 2. This we can express as the root of 9 multiplied by the root of 2. And this we could express as the root of 11 multiplied by the root of 2. Which law of indices are we talking about? The law of indices that we're referring to is this one, where we know that, how are we going to put it? We're going to say that AB to the power of n is equal to a to the power of n by b to the power of n. Right? We discussed this in one of my previous videos as well, where we spoke about indices and we had different rules of indices. This was one of the rules that we referred to. If I make n equal a half, then I can say that ab to the power of a half is equal to a to the power of a half by b to the power of a half. And if I replace the index of a half by the square root sign, we also discussed that in the videos on indices too. I can write it as root of AB is equal to the root of A multiplied by the root of B. Right? This is a foundation of the indices. You'll be using this so often, best get familiar with it. Right? So this is the general rule. We make n equal to a half and then we just change the notation. So instead of using the power, we use the square root sign. And this is what we end up with. Alright? So using the rules in green here, this is what we get here. Now, this is what it is. This is what it is. However, with these guys here, we have something that we could work with. Because we have 4 here, we know that 4 is a perfect square. And we have 9 here. We know that 9 is also a perfect square. So in other words, let me clear the board here now. In these 2 cases, we could go one step further and say that this is equal to 2, which is the square root of 4, multiplied by the square root of 2. And here, we could go one step further and say that this is equal to 3, which is the square root of 9, by the square root of 2. So we were able to move from root 18 to 3 root 2. We were able to move from root 8 to 2 root 2. The reason we were able to do that is because in the process of simplifying these 2, we made use of the fact that both of those numbers, 8 and 18, we could express both of those numbers as the product of 2 numbers where at least one, well, it had to be 1, because if you have 2 perfect squares, you just be going around in circles. So for it to end up being a surd, one of the 2 numbers has to be a perfect square. If you have 2 perfect squares, you'll just end up back up with an integer, which would be not the point of what we're discussing here. So if you have a surd, in other words, you have a root of a number that is not a perfect square. 8 is not a perfect square, 18 is not a perfect square. But within those numbers, you have a factor somewhere that is a perfect square. Then you can simplify the original surd using that particular property. So this is another place where your basic maths enters the picture, because the understanding of factors and multiples and all of that allows you now to sit back and say, well, all right, let me see if there is a factor of this number that is a perfect square. If you can find a perfect square among the factors of any number, a number that is not a perfect square itself, then you have the foundations of a very elegant simplification of the original surd. So we get from here and here to here. So I'm going to do a few more examples to illustrate the point that we're making here. So we started with 8 and we started with 18. How about 45? Let me say 45. Right? Let me try a different number now. The square root of 45. We know that 45 itself is not a perfect square. So the square root of 45 is a surd. But we know that 45 is 9 by 5, not so? Yeah? So the root of 45 is equal to the root of 9 by 5. Right? Which is equal to the square root of 9 multiplied by the square root of 5. The square root of 9 is 3. So your final answer here would be 3 root 5. See how nice it is? It's nice or no? It's nice. We're going again. Let me say we want to use the number 288. Big number this time. Right? So we want to find the square root of 288. The root of 288. We know that 288 is 144 by 2. So the root of 288 is equal to the root of 144 by 2, which is equal to the root of 144 by the root of 2, which is equal to 12 root 2. And we could do that with any surd. Sorry, we could do that with any, what I refer to in another video as an imperfect square. Sometimes you have to use your own vocabulary in the absence of other known vocabulary. So in a previous video, I spoke about perfect squares, and all the numbers that didn't fall into that category, I refer to them simply as imperfect squares. So let us go back there. So in other words, if you can express an imperfect square as the product of a perfect square and another integer, then you can simplify the surd. You can simplify the square root of that imperfect square. And yes, your final answer will in fact be a surd, a different type of surd, but we come into that just now. We almost at the point of wrapping up. Let me do a few more examples just to illustrate the point. Let me come back in the middle here now. So we started with root 18, we started with root 9, then we went with root 8, sorry. How about, let me say, the square root of 24. How about the square root of 24? The square root of 24 is what? 24 we know is 6 by 4. Alright? 6 by 4, which is root 6 multiplied by root 4, which is equal to root 6 by 2, which is equal to 2 root 6, right? 2 by root 6 is 2 root 6. Let me try the next one now. Let me see. Hold on. I got a nice number here now. Have it. Hold on. Right, so if I want to find the square root of 507, right, I just choose a big number just to deliberately drive home the point, right? You wouldn't usually have to deal with numbers of this magnitude in an exam, but we're making the point here, so we want to use a range of numbers. The square root of 507 can be expressed, if we are aware, as the square root of 169 multiplied by 3. And if we know that the square root of 169, well, this of course will be the root of 169 multiplied by the root of 3. Yeah? We know that root 169 is 13, so the answer here is 13 root 3. End of discussion. Yeah? So in other words, again, I'm going to repeat. Yes, repetition is part of how we teach sometimes. Once you have an imperfect square that you're trying to find the square root of, if you can find among the factors of that imperfect square, assuming of course that it is not a prime number. So in other words, trying to find the square root of 23, you can't go further than that. 23 is a prime number. But if you want to find the square root of 24, boom. Yeah? So if you can find among the factors of that imperfect square a perfect square, then you could factorize. So in this case, the perfect square was 9. In this case, the perfect square was 4. In this case, the perfect square was 169. In this case, the perfect square was 144. Once you could do that, you could break it down. And eventually, you'll get a surd looking something like this. Right? You get a surd. In this case, it was 12 root 2. In this case, it was 13 root 3. In this case, it was 2 root 6. In this case, it was 3 root 5. Which leads us into the discussion of different types of surds. And we will deal with that in the next video. Stay tuned.